this graph key and answer any questions that you might have that you can't kind of figure out from my work. So this first one, it's a velocity versus time graph, and they're all the same scale, and we want to know the greatest change in position. Right? We know that how you change your position is accumulating a velocity over a time period, right? Going 5 meters per second for 4 seconds makes you travel a distance of 20 meters. So this case, we can't do the easy ones because most of these velocities are changing. However, we know that this equation, this mathematical equation, says exactly what I just said about position. The displacement of an object is equal to the integral or the accumulation of velocity over a time period. That's what this symbolically represents. And from a geometry point of view, we're looking for then the biggest area. Think about it from an algebra point of view. We want to be going the fastest for the longest amount of time, and that's this guy. This guy's stopped jogging, sprinting, right? You're not even going fast the whole time. This one you're going fast at the beginning and almost stopped at the end. This one you're starting from rest and then getting faster. This one you're starting from rest, getting faster, and then getting slower. This one, you're going fast the entire time. And so you're going to get a bigger area, thus a bigger change in position. Biggest area, when looking at a velocity graph, leads to the greatest delta x. All right. When is acceleration most negative? Okay, acceleration is the rate at which we change our velocity. So when we're looking at a velocity versus time graph, the acceleration is the slope. We want to have the biggest negative slope, which is right in there. Remember, acceleration is how we're changing our velocity. So it's the slope of a velocity graph. And then we want it to be the most negative. This is a position versus time graph, and we want to know what interprets. Okay, so looking here, this looks like, I'm not even looking at the answers yet. This guy starts at rest, moves to the right at a constant rate, so it's got a constant positive velocity, and started at the origin. Okay, I didn't mean to say it started at rest. It started at the origin, and it's constantly moving away at some constant. So we're looking at that one. Right? The object is moving with a constant velocity. It happens to be a positive velocity. The object started at the origin, but this one describes it the best. All the other ones are wrong. Okay, same concept as that first one. An elevator moves from the basement, yada, yada, yada. How far does it move during the first 3 seconds? Again, well, at 3 seconds, it's moving 4 meters per second. At 2 seconds, it looks like it's like 2.8 meters per second. At 1 second, it's only moving maybe 1.5 meters per second. It's traveling at different velocity at different time periods. However, we know that if you accumulate all those velocities over time, delta x is the accumulation, the integral of velocity over time. That will give us the change in position. We want the area under the curve, and this area happens to be just a triangle, and the triangle is a 3x4 triangle, which leads to an area of 6. Thus, during that time period, even though we were going at different velocity every moment, we did travel a total of 6 meters during the first 3 seconds. Number 5. All right, we want to know the velocity at 2 seconds. Again, we want to know the instantaneous velocity, not an average velocity, the instantaneous velocity. So you come over to 2, and we want to know the slope at that moment. Okay? However, the slope there, since this is linear, the slope there is the same that in that entire line. And so what'd you do? Well, you went 5 meters up, and it took you 2 seconds. So you traveled 5 meters in 2 seconds. That's 2.5 meters per second. And the rate, the slope at 2 is the same thing in this case as the slope during the first 2 seconds. Okay, after that, it starts to bend and the velocity slows down. But the velocity at 2 is really, really similar to the velocity during that first 2 seconds. So this is velocity as a function of time, and we want to know the acceleration. Okay, so if you're looking at velocity versus time, acceleration is the rate at which we change velocity. So the acceleration is the slope. So all I'm doing is estimating the slope at that moment. And it sure looks about at that moment we are going what, up 10 and over 30, up 10, right? This slope is really, really close to the slope at that point. And so then we get a slope of 10/30ths, and we get, that's just 1/3. And again, these scales, you got to be careful. The scales are not always the same. Same thing up here. All right, 7, the motion of an object. We want to know the magnitude. Remember, magnitude means size. We just want to know the size of the acceleration. And we want to know the instantaneous acceleration. So all we want to do is we want to know the slope at 65. So we want to know the slope right there. Well, the slope right there is really, 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 really close to 1. Okay. It goes over 10 and up 10. It's weird because these scales are going up by 10s and these are up by 5s. So this is actually over 10, up 10. Just be careful. It's all about the scale. But again, the instant acceleration at that point is really, really close to that entire slope. And that slope is 1 meter per second squared. Here's a graph of an object's position. Which sentence correctly describes it? Okay, so I'm not even looking at the answers. And if you look at this, this is position versus time. So during this first period right there, I'm not actually doing anything. I'm just standing there. Then I'm going left back to the origin. And I get back to the origin. And then I'm standing still. And that's what that looks like. Okay? Again, this is position versus time. The slopes are velocity. 0 velocity, negative velocity, 0 velocity. Standing still, moving left or backwards, and then standing still. Okay, what's going on here? An object starts from rest and undergoes positive constant acceleration for 10 seconds and then continues with constant velocity after that. Okay, so if we know we have constant acceleration, we have to have a positive curvature. It's going to look like a quadratic. It's going to look like a smile at the beginning, because we know that if we're accelerating, we are increasing our velocity, so our slope has to get bigger and bigger and bigger, right? It should look like this. That's what a positive acceleration looks like. And then after that, we continue with the constant velocity. Well, that just means our slope should be constant. And I don't love this picture, but it really should be like concave up smile and then linear. That's kind of what that graph should, in theory, look like. And again, it just does it really quick. All right, we want the smallest change in velocity. Smallest change in velocity. So again, go back. Earlier, we were looking at the changing of a position based on velocity. Now we're going to look at the changing of a velocity based on acceleration. We want the smallest. So from an algebra point of view, if you want the smallest change in velocity, you want a really small acceleration as often as possible, and then you won't get a change in velocity. So in the geometric point of view, we want the smallest area. The area under the curve, I kind of highlighted everything there. That area right there represents delta V. It's accumulating your acceleration over a time period, which changes your velocity. This would be a huge change in velocity because you had a monster acceleration for a long time. This would be the smallest. 11, position versus time graph. Okay, so looks like we are jogging away. We are standing still. And then we are, looks steeper, so then we're running back. Again, jogging, standing, running. And how do I know that? Well, I'm looking at the slopes. The slopes here are velocity. And again, I'm going to the right, I'm standing still, and I'm coming back to the left. And so if we look at that, we want a positive velocity to the right, 0 velocity when we're standing still, and then I want a monster negative velocity when I'm running back. And you can see this is lower than that is high because we were jogging and then running. Jogging small, running bigger. Right? This needs to be more negative than this is positive. Okay? And again, these are constant slopes, which is why this is a constant line here and a constant line here. All right, noting the different axes. Which of the following represents motion at a constant velocity? Well, this is a position versus time graph. So velocity is the slope, constant velocity. Check. This one, this is a velocity versus time graph. Here the velocity is increasing. Okay, well, that's not constant. Yes, this is velocity versus time. Velocity is constant, it's just chilling. Here, the acceleration is changing, which would clearly, even if you were at a constant acceleration like this one, even a constant acceleration is constantly changing your velocity. Thus, you do not have a constant velocity. And this is a changing acceleration, which would also cause a changing velocity, which would make your velocity not constant. Okay, so just these two. These two are really the same graph. All right, position versus time, and I want to know which object had the highest instantaneous velocity. So I'm looking for the biggest slope, right? Biggest slope. We know that velocity is the rate at which you change your position. And so for like this one, you're jogging the whole time. This one, standing still. This one, walking, jogging, running pretty fast. But this one, walking, jogging, running, sprinting, and really fast at the end. That is the steepest of these slopes. This one would be jogging away, slowing down, standing still for a second, jogging back towards the origin. And you ended up right where we started. Okay, but this has the biggest slope, so it's got the biggest instantaneous velocity. 14, we are looking for velocity over time. Thus, the acceleration is the slope here. So we have a negative acceleration, zero acceleration, because the velocity is not changing, positive acceleration, zero acceleration. Acceleration is the rate of how we change velocity, meaning it's the slope on that curve. So we need the acceleration, like I said, to be negative, 0, positive, 0. That's what these four little phases look like. The following graph represents acceleration during those 5 seconds. Okay, so if you have an acceleration of 0, you have no change in velocity. Then you have a monster negative acceleration, which means our velocity decreased. No change in velocity, small increase of velocity, right? That's the definition of 0, negative acceleration, 0 acceleration, positive acceleration. So let's look at a velocity graph. Remember, acceleration is the slope. So no velocity change, velocity has to be constant. Decrease of velocity, okay, make our velocity go down. Then here, when we have a 0 acceleration, we must be here. No change in velocity. And then we increase our velocity, and we increase. So no change, decrease, no change, increase in terms of velocity, and that corresponds to those 4 different accelerations. Looks like we're going back to area on this one, right? The change in velocity is the area under the curve, right? Accumulate acceleration. Acceleration times the time gives a change in your velocity. So we want the area of the curve, and the area is just a triangle that's 3 by 3, and we get 4.5. The velocity at 3 seconds. We want the instantaneous velocity at 3 seconds. So I need to find this guy's slope right there. And pretty much it's, down 10 over 3. So that's a negative 10/3 slope. So then a negative 3.3 meters per second velocity. And again, it's traveling that velocity that whole time, but certainly at that moment. Looks like we're back to the area under the curve again. We want to know the distance we covered, but our velocity is changing. Again, if the velocity was constant, we'd just go back to algebra 1. We would just take a velocity times the time and we'd be done, right? 10 meters per second, 4 or 5 seconds, you traveled 50 meters. But this is big boy physics. Our velocity is changing, so we have to use calculus principles. And in this case, we have to find the area under the curve, and this is a triangle that is both 2 by 5. So that's just saying this. That's the area of a triangle. 5 times 2 times a half. 19. Consider in the following graphs. Note okay, so this is position, this is velocity, this is acceleration versus time. So keep track of all these. Position versus time, this is a constant slope, so a constant velocity with an acceleration of 0. This has a changing velocity, happens to be constant acceleration. This is 0 acceleration, right? No change in velocity. This is an increasing acceleration, and this is a constant acceleration. So the constant accelerations are those two guys. Constant slope, constant value. But again, we're looking at acceleration versus time and velocity versus time. Looks like, what do you want to do here? I'm just, oh, how far does it move? I'm just looking at the area under the curve, which looks like I highlighted it here, right? That area, I mean, you're traveling 3 meters per second for 4 seconds, so of course you go 12 meters, right? That's about as easy as area gets, because it's just old school, right? We were just going 3 meters for 4 seconds, or excuse me, we were going 3 meters per second for 4 seconds. Of course we went 12 meters, and we did go to the right because it was a positive velocity. All right, looks like this is the last one. This is the graph, velocity versus time. You can see has a negative slope. So it's a constant negative acceleration. So yes, the best interpretation is the object is moving with constant acceleration. The acceleration it's not increasing or decreasing. It's not increasing its velocity. It's not moving at a constant velocity, and clearly the object has velocity, so it is moving. Okay? Hopefully this helped you with these things, and check your answers, check the key, and see if we can get started on some good graph stuff.